Hello, everyone. Uh, I'm going to review the questions of the week 9 tutorial part. So the questions are like the first one, second one, and third one. I will review the questions, the solutions, and any other corresponding materials. And if I need, I will use the references from the lecture notes as well. Okay, so I prefer to use my own handwriting. So the first question is the same here. So an ODE in the format of y prime equal f of xy, where f of xy is equal to 2x minus 3y plus 1 is given to us. So the analytic solution is given to us, and the part A asks us to find the local truncation error in terms of C and H if we use the Euler's method. So, so the keyword here is the Euler's method, and all right. So the Euler's given to us. So this means H is the step size here, and C is the uh, belongs to this interval. And if I refer to the lecture notes, so week 8, so the week 8 and so section 2. So it says that numerical approach. So we know that from the Taylor's theorem. So we can review the Taylor if we deal with the ODE equation, and it is in the form of y prime equal f of xy, and we can implement a numerical approach for solving this ODE. So the first order of that, um, like we can use this term and this term, and the first order, I mean, like m will be 2. Okay, so from the Taylor theorem, uh, so the third term here, second derivative, where psi belongs to the a between a and x. So and h is the step size again. So we can use this one. So this will be the classic Euler's method, and the third term will be the local truncation. So here, therefore, we will use this one and we will calculate this one. So h squared is obvious, 2 factorial is obvious, and so what are all we need? We need to find y double dash. So y double dash we can use like this y of x because the analytic solution is given to us, and it is easy just to derive twice and to get y double dash. And or we can use this one as well. So it might be a little bit easier. So anyway, y double dash is equal to, using the first one, 2 minus 3y prime. So derivative of this guy is like 2 minus 3. The derivative of y is as a dependent variable. It will be y dash or y prime. So but y prime of c itself can be obtainable by using this guy here. So it will be by substituting this y prime c by 2x minus 3y plus 1, and substituting x by c. It will be 2c minus 3y plus 1, which is also written here. And then rearranging, and we can get this one. Or it is like just take derivatives twice from this expression. So you will be able to get the same result. All right, so we've got this one. Now let's use the third term, and as I showed here, this one as well. So there is psi is the C, the same thing. All right. So h squared over 2 y double dash of c h squared over 2 38 e to the minus 3c minus 1. So uh, it will be this one. So it will be this expression, which is in terms of h and c. Okay, now let's go for part B. So part B, like part B is here. Okay. And it says that find a bound for the local truncation in each step if h is 1/10. Uh, if step size of the 1/10 is used to be able to approximate y of 1.5. So let's remember that the initial condition is given. So y of 1, and it says that step size of 0.1. So it means like repeating 5 times like using the Euler's method to get y of 1.5, because 1.5 subtraction with 1 will be 5/10 divided by step size will be 1/10, 5. All right, so let's go here. So part B, so in this process, C or psi will be belong to the 1 and 1.5. So to find the upper bound for the or bound actually. So we will use the step size h. So 19h squared e to the minus 3c minus 1. So e to the minus 3c minus 1 is a decreasing function because it's like e to the minus t. So it's like this function here. So in this interval, if I choose the number on the left or like c equal 1, I will be able to get the upper bound for this guy. So substituting h by 1/10 squared 19 e to the, so instead of c, I will take c as 1. So this will be e to the minus e power 0. So the answer here will be 19 over this guy, so 100. So as I said, we do 5 times. So at first repetition, so this guy is h equal 1 or 1/10, 0.1 to be able to get y of 1.5. So we use 5 times Euler's method. So at first time, c will be belong between 1 comma 1.1. So if we refer here, c is belonging to the, like in each interval, it is belonging to xn comma xn plus h. So means 1 and 1 plus 0.1. Okay, so that's why I have written the same thing here. C belongs to 1 comma 1.1. And as I said, e to the minus t, or 3 times c minus 1, is a decreasing function. So for this function in terms of c, by choosing c equal 1, it will be upper bound for this guy, which is like e power 0 equals to 1. Now, in the second step, c will be belong to this interval xn comma xn plus 1, or xn comma x n plus h. So c will be belonging to this interval. Therefore, again, e to the 3 minus 3c minus 1. So upper bound will happen in this interval. It will happen by choosing c equal 1.1, and like and this is definitely less than if I choose c equal 1. Okay, so it will be again 1. So again, third step, this c belongs to this step, to this interval, and so since we need to five steps, so um, we can still choose c equal 1.4 to get the upper bound, but uh, it is okay if we choose c equal 1 still. Okay, so anyway, and these are the extra explanations, and the last answer is this guy. All right, and the same thing is happening with h equal 500, 0.05. So here you just need to replace h by 0.05. So it will be this guy. And again, so the answer will be 19 over 400. So I mean, just in my head, like I just replaced h by 0.05. That's fine. All right. So now we can move to the part C. So it says that calculate y of 1.5 using the shown step size using the Euler's method. All right. Here, let's review the first step. So we can obtain y of 1.1 equal to y of 1 plus h y prime 1. Where did I get this one? So can I come here? So it is y n plus 1, y of 1.1 will be equal to y of 1 plus h times f. F is like y prime. Okay. So I just use the classic Euler's method, and yeah. So I mean, if I want to do the first step, is like y of 1 or y of 1.1 equal y0 plus h times y prime. So f is like y prime here. All right, move on. So y of 1, the initial condition, if you remember, y of 1 is equal to 5. Replacing these things, y prime 1. So y prime 1, I just used this one here. Y prime 1 is 2 times 1 minus 3, 5 plus 1. So let's see, 2 of 1, 2 times 1 minus 3, 5 plus 1. Okay, so calculating this one will give us 3.8. So again, for now in the second step, y of 1.2 equal to this guy plus h times y prime at 1.1. So let's go to the Sage Math. So can I have Sage Math? All right, so Sage Math is here. Also, I've got a web version is here as well. So I use MacBook. I installed Anaconda, including all the packages, including all the Python. Then it has got like Jupyter Notebook. So when I call the Anaconda, it brings up the Python and Jupyter Notebooks. So then after that, I'm able to call my Sage Math. So it will use the Jupyter Notebook, this guy here. Anyway, week 9 question 1, it's here, y prime, the initial condition, analytic solution, and part C, focusing on calculating y of 1.5. All right, so we can use package, but I prefer not to use that, which I explained in week 8, and it's like using our own algorithm, which is faster and efficient and fancy, of course. So we can use it. So let's define a function and let's call it in like meaningful name, Euler. And we will gather all the xy in the list, which we can call it list parentheses or bracket open and close, or like we can write in this way, PTS equal to broken bracket or bracket, empty bracket. Initial condition it's here. Okay. So the initial condition is this guy, x equal 1, y equal 5. Variable, so all the pairs xy, they are variable. So pt, so means pt is equal to the vector. So vector of the list of the vectors of xy, 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 so 5 times. So every time when we found, if you find the point xy, we will put it in the list of PTS. The command is given here. And how many times do we need to repeat this process? Well, 1.5 minus 1 divided by h. So h is here. So 1.5 minus um, minus 1, like x here. So it will be over h, 1/10. So I've got just int integer here, and since it's Python or Sage, I will add +1. So this will repeat from 1 to 6, not including 6. So in fact, it will repeat this process like 5 times, just 5 times, which we need. So K1 is the f of x, y. So K1 is like this guy here. So it's this one. Okay. Or I can show it here. Where is that? Okay, course note. K1 is this one. I called it K1 because in the improved Euler we need K2, and in the Runge-Kutta order 4 we've got K1, K2, K3, K4. Okay, so that's why. So it's not a big deal. So you can just, if you want, you can just ignore this part and you can just write here f of f x y. Anyway, so this is the definition of the Euler's method, yn plus 1, updating by previous y plus h times this guy. So it's not like canceling these y's together. It's in the computer programming, we write the previous y like this one, and it's updating new y, and hex x will be updated by adding one step size to the older x. So once we found these new y and x, it will be here. Yeah, it will be in xy here. And so it will be a point, so point, and we will add those points to our points PTS here. Okay, so then after this one, all we've got a PTS, like a list of the points. I will extract the list of the points of the first components in one list and second components of the points in another list. So the first one is x, and the second list will include all the y's. So again, it's possible to write these things like maybe better. Well, it's okay. But this is like obvious that points. So we will extract these things here. All the in first component, 0 in Python or SageMath means the first component will be inside PTS1, and second components, I mean y's, will be inside of PTS2. Okay, so we can apply this one. We can do this one, and it will be 1.1 x's, x 1.3, 1.4, 1.5, and the corresponding 3.8, it is exactly this one here, sorry. So this guy is the same thing that we've got here, 3.8. And if we continue, we will get this number here. Okay, so how about like this step size here, 0.05. So, you know, our function is depending on the h and b. So H is the step size and B is the target. One Y of 1.5. This one is the B. Changing the step size will tend us to have slightly different and finer and more precise solution. So when X is 1.5, using the step size, finer step size, we will get this guy. All right. Now let's go to the questions. Where is the questions? Are here. Part B, it says that calculate the error in part C and verify the global truncation error. So global truncation in error in Euler's method is big O notation of H, means like a constant something times H. All right, so we will do that. So exact using the analytic solution that is given to us from the question here, we can use this solution to get the real solution or the exact solution of the y of 1.5, and we can compare what we have done using the Euler's method and how far our exact solution from the real solution. All right, part D. So y of 1.5 using the analytic solution will give us this guy here. And using the step size of 1/10 is like the subtraction of the exact solution and the numerical solution using the step size of 1/10. It is this guy and it is this one. And the subtraction is this one. And of course, we are after for the absolute value because, yeah, we just need to know the difference. And the difference is always like a positive animal. And again, we can use the same process for using y step size of the final step size, like 500. So it is this guy. Okay, so there are something is written here. So I will apply these things here. We know that the global error is the big O notation of H. And in other words, H gets finer, the global error truncation will be better by this much. Big O notation of H, or C times H, where C is just a constant. Okay, global error notation, like big O error, global error of for the step size of H1 and H2 is just 2/10. All we did is just dividing this guy by this one, and it's been like 2.1. So it's been like this one. Well, we can see that the blue things that I have written here is like error H1, OH1 over OH2. So it's like OH1 is like C times H1 or something like H1. So like, and the other one is like C2H2 or something else like times H2. So roughly speaking, so let's put like this one. So we can cancel them and 1/10 over 500 will be 2. But we know that is like something or C1 here and C2 here, they are not the same. So they are not really cancelable, but they are almost closer to each other. So that's why 2.1 in the numerical calculation, but in the theory, we expect something like 2. So almost 2. Okay, now here, before going to question 2, this is the PDF version of not this one, Jupyter Notebook, which I have printed like the same thing that we've got here. So we can see this one. Okay, so let's go here, part D. So it's the thing that I just explained here. Okay, I'm going to look at here. So analytic solution is given here. It's the same thing that I have written this guy in here. So analytic solution of, so once you define this one here, so it is easy. If you could do this one in Python, it could be a little bit hard. Now in SageMath, it's a little bit easy. So y of 1.5 or analytic solution of 1.5 is this guy. Okay. So that's why, so can I go to here? So it's the same thing, it's same number here, 2.0532. It's the same thing here. I just copied from this guy to, and I wrote it here. All right. Now, first error or EH1 is like absolute value of analytic solution minus, where did I get this one? So I just got this one from here. This guy, I just copied that one. And analytic, so it is, the answer is this guy. So that, yeah. And if I get the second error, so, or this guy, where are you? This one. I just got this number by this one from here. Okay. Not that number, or that number I put it here. So no, it's the same thing. Okay, so almost the same thing. Sorry about that. And it's not 85, it's just 9. And if I divided that one, so I will get this one. It's the same thing. Okay, and also another thing for your information, instead of writing XY polynomial ring, your name, so we can write X is variable, Y is the dependent variable like this, and we can use Y prime minus, put everything on the left-hand side, and using the initial condition, X equal 1, Y equal 5. So still you can get the same analytic solution as it's here. It's this one here. So in case if this one was not given to us, we could still be able to obtain it. And even without this one, still we can use this process to get the local truncation. So we really do not need analytic solution to be able to get the local truncation. So yeah. All right. So back to the question 2. Let's go question 2. Okay, so it says that explain that why this question is tough in implementation by using Euler methods. Well, there is exponential e to the minus t. It's 1 over exponential of time. So in numerical methods, in numerical analysis, we don't want anything closer like 0, and also in the denominator. So it's hard for the computers to handle it. So it's the first order linear ODE. We can like get the analytic solution. Okay. And let's go to the analytic solution here. Okay. By the way, you will be able to see extra explanation in your PDF solution. I'm giving extra ideas here. So again, using our fancy algorithm implementation, Euler's method, so y prime minus 6y plus e to the minus t. Well, you see that from 1/10 and y of 1, we can still code it up using this powerful implementation, and we can get the answer. Okay. So that's one thing, and we can still get the, we can still also use the, like this one is the Euler method, forward Euler method. Okay. So minus 6y e to the minus t, and I just changed this one. So it's the same thing, yeah? So it's the same thing here, and I just changed this one. The rest are the same. Now, what about this one? This is the backward Euler method. So the backward Euler method, so that's why you can see minus one here. Slightly different, it's the same thing, yeah. And yeah, it is also easy to write it. So next week you will see the limitations of the using forward Euler method, but there is no limitation of there is of course limitation and advantage of using the backward Euler method. So the step size of using this guy should be finer. So can I try this one? So let's do this one time. It's been used and it's this one. Okay. So now I wanna do this one here. Let's have finer version 5, and it's still doable here. 0 point, same number here. And what about this one? 0 0.1. It's just this one, and let's use just one step. It's awful. Okay. And this one, and let's use this one as 0 0.05. Okay, the answer is this one here, and the answer is this one here. So, well, you see the difference here. So this guy and this guy here. And I can maybe use 0, 1. So it will be a little bit. Okay, sorry. And just only this one, I just scroll down here. And the difference is this much. So let me do the previous one again. So all I need just to do that one here. Okay, so it's just 1. Okay, so the answer here is this guy. The answer in the like using 2 steps, the answer will be 0 0.082. The answer using 100 will be 0 0.073, and the answer is using 0 0.01 or 1 over 1000. And the answer will be this guy. Okay. Yeah. Now, it's stiff to handle this ODE, but how about using the package? Yeah, let's use the package. So if we use the package, you will see that there is like problem here. Okay, so the package uh, won't be able to do this question. By the way, if we want to do we can still also use the DE solve and get the analytic solution. Okay. Yeah. And the analytic solution, we can define it here, and this guy here, copy this guy, and you put it here, and then use the analytic solution like to understand this guy 100, and it will be this one 7.44, and this will be 7.36. Okay. All right. This is the question 2. Using forward Euler method, we should use finer step size, but for backward Euler method, you can still use it for any step size, but it will be slow. Backward for any step size, but it will be slowly. I will talk about the forward Euler method and backward Euler method at the end again. All right, so let's move to the question 3. Okay, so I will come back. We will come back here again. And by the way, the PDF of this guy will be shared as well. Okay, question three. So question three here. So it says that y prime of lambda times y in this format. So where lambda is just 2. So y prime of equal to y. So it is easy to understand that the analytic solution of this guy is y equal exponential of 2x. So it says as it's asking to calculate y of 1/10. So the initial condition is like when x equals 0, y is equal 1. Just one step. So one step, when it says one step, it means h should be equal 0.1 to get from 0 to 0.1. And use the Runge-Kutta order for method to approximate this guy. Okay, so we will use it. So again, I will use the same thing here. So let's go here. Can I, this guy? No, here. The Euler's method, for forward Euler's method, it's this one here. And I just copy that one and I put it here. So this will be Runge-Kutta HB. So for sure you can do in a different way to define your variables. F of x is as the same thing. Okay, I'm enlarging. Runge-Kutta, for sure, it's the same thing. PTS instead of broken brackets, it's like round brackets using in this way. So it's okay, you can do it. Y of 0 is equal 1 because of the question. Y of 0 equal 1. So it's the same thing here. Same thing, variable PT. PT will be the points. So PT, a variable point, and it's that variable, that point, and every point on the plane is just, it has got X and Y. And we will put those points inside the list of the points. Okay, so the list of the points is defined here. It's empty at first, and we will do it again. Okay. All right. So again, the same thing. Can I go here? So this is implicit Euler method. How about Runge-Kutta? I don't want that. Okay, so Runge-Kutta, I couldn't find it here. Can I try the other one? Okay, so Runge-Kutta is here. So you've got, we should have actually K1 and K2 somewhere. Okay, so K1, K2, K3, and depending on the way that you define alpha to beta, alpha and alphas and betas, you can get different Runge-Kuttas. The famous one, I just applied this one. So do you see the K1, K2, K3? So K1 is the same thing familiar to us. K2 is xn, h over 2, yn, h K1 over 2. So back to the stage, x plus h over 2, y plus, okay, h times k1 over 2. So is that the same really, y plus h? Yeah, y plus h times k1 over 2. So it's the same thing, h times k1 over 2. And k3 and k4, they are really like, I just follow these things here, k3 and k4. Yeah, okay. All right, so y equal y plus h times k1, 2k, 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 3k, 4. And it's just coming from here. Yeah, it's coming from here. Yeah, this guy. And I will update my x by, again, the same thing. So just follow them. The rest are the same. The rest are the same really, and I just applied this guy here. I just ran it just I run it now, and it's the same thing here. It's happening here, and this is the answer of y of 1.1/10, y of 0.1, and this is the same. This is the answer. Okay, so let's go to the questions. Okay, so that's done. Okay, it says that find bound for the local triangulation. Luckily, it's given to us. Order for, so it's like this guy is given to us. So this part, but this part, so roughly speaking, it's asking us to find an upper bound for this part. So it's the same thing as the question one part A. So it's this one, just like, it's just um substituting h by 1/10, 5 factorial, okay. And y power 5, it's just easy, just take the derivative of like this one 5 times. Oh, since it's exponential, we are just lucky that it's writing exponential 2x, and this 2 comes to here like 5 times, so it will be 2 power 5. So that's why this will be, here is 32 exponential of 2x. So again, substituting h by this guy here, 5/10, and c is belonging to this interval here between 0 and 1/10. Now, exponential of 2c or exponential of 2x is just increasing function. Okay. Therefore, since it is strictly increasing function, I will just get this one. Last time I had to take the left number, but this one, it is strictly increasing. So I will get c equal 1/10 to get an upper bound for this one. Okay. So it is this guy, and the answer is this one. Okay. Very easy. Now, part C, approximate y of 1/10 using two steps, means h should be 0.05. So let's go to Sage. Okay, so Sage Math. By the way, I just for this number, yeah, it was, I just cheated from this part. 1/10 h. So it's this guy, 1/10 power 5 over 5 factorial. I was for this is my calculator, this Sage Math, and yeah, it's the same thing here. This is 3.25, these things. Okay, and also we can do these things. Exact solution, exponential of 2x, and exact solution is this guy. So if I use the exact solution is e power 2x. So instead of x, put just 0.1. So it doesn't matter if you write 0 here. So it will be this guy. Okay. Now, if I try to understand, so can I use this guy here? Okay, it's this one. It says that, sorry, it's just C. Yeah. Yeah, I think I messed up something about something, like I thought that it's like it says that y of 0.1 with using two steps. So I just read this question rather than part C. So part C, it says that compare the error in y1 with your error bound. So okay. It's good. So let's not run this one. Okay. So Upper bound is this guy. Okay, upper bound error should be like, it's really local error should be really like this one. Exact solution e power 2x, it's this one, x equals 0 0.1, and the answer is this guy. So the answer of e to the 2 times 1/10 is this guy. Now, solution of one step. So if I use this guy here, solution of this guy here, 1/10 is this one. So solution is this one. Now, global error. So not global error. It's since it is one step. In one step, global error and local error is the same thing. So getting the subtraction of the exact solution, which is coming from here, and the solution one step, it is just here, or I just got it from here. So getting the subtraction, so the subtraction is this guy. Okay, so this guy is the actual error is this one, but it says this is the local upper bound for local error. So this means like in the worst scenario case, we will get this much error. But our algorithm was a little bit better, so it worked better. So because 2.75, this much number, e to the minus 6 is for sure is less than this guy. Not too less, but it is still less. Okay. This is part C. Okay, comparing the error y1 with the error bound. So this means like really upper bound local error is really true because the actual error we calculated by comparing the analytic solution and numerical solution, subtracting them, taking the difference, we see that the actual difference or error is this guy, which is less than this one. Okay, move on. Part D. So part D, it says that use two steps, means his step size will be 0.05. Okay, let's do it. So it's I've written here, so I won't just wanted to write about this guy here, 0.5. I can still do. So it's this one for sure. It's like finer than this one, better than this one. And yeah, it's the same thing here. Yeah, step size h just changed and 1/10, 0.1. Okay, so let's do part E. Part E, so this guy is checked, this one is checked. Verify the global error, global truncation error for this guy method is of order H4 by comparing the errors in part A and part D. So yeah, so let's do this one. The global error truncation of the Runge Kuta order 4. RK4 is, according to the lecture note, is this guy. OH4. Can I find it somewhere? Um, yes, it might be here. Okay, it's not here. Higher order, second order, fourth order. No, it's for the systems. Okay. Anyway, it's OH4. So OH4 for order M4. So let's go back here. Okay, so 1/10 and H2 0 point. So we should get this one. This is well explained here. Nothing to be worried. So it's C1 H1 or something times H1 power 4, something times H2 power 4. So it will be C1, C2, this guy, 2 power 4. So almost cancellation for these things. We expect something like 16. Now but the one that we will see, it is like 14.72. So closer to 16. Back here, okay, Rungekuta 0.05 is given here. Part E, solution, one-step solution using H 0.0, 0.1 is this guy. Two-step using the step size of the 0.05 is this guy. Analytic solution is exponential of this one. So this is the exact solution. Now error of that one is one step is this guy. Subtraction of exact solution and one step. Two step like using the step size of the 0.05 is this guy. It's this one. Now, I do this one here. So all I just do here is calculating this one, this guy here divided by this one. Okay. So if I go here, so this division means like this one, 14.72. So which confirms like 16. It is closer to 16. Okay, here's the thing. So actually in question, so here you expect something closer to 16. And here you see something like part D, please. It's 2.1. If you see something like a number like very better than this one, like E sub 0.1 and E sub 0.05. So this division, if it is like even very more than 2, still it is okay. So this means your method is like working even better. Okay. So it is possible to see sometimes that it is 16. It is possible to see in some examples that the method works even better. Okay, so if you see something like even better, like this, a number like very bigger than 16, so no worries, your method is still okay. It works fine, and it works even better. Now let's go to stage math for extra explanation. Back to the question 2. I said that. So it's possible to see that, as I said, in using the package of the Euler, like Sage Math, it's not possible to solve the ODE given in the question 2. If you use the Euler method, so this is the analytic solution Euler method with the step size of 0.1 and step size of the 0.3. You see, the blue one is the original T plot, the analytic solution. The step size of the 0.1 is the red one. And the step size of the 0.3 is like this green one. It's oscillating, but it is okay. It's gradually it takes a lot of time, but it's kind of converging. Now, if I get the step size of more than 0.3, like 35, actually more than 33. So if this one is the analytic solution, your numerical method with using forward Euler method, it's diverging rather than converging. It's diverging. Okay, this one was for the question 2 for complete explanation. In Canvas, there is a file called Week9 optional file with using the Sage Math. So you can see other examples here so it's the same type questions of the question 4, so you can use this one. This method, and you can see that again, I have used the same thing. So we can solve it. And we can again start to test these things that, yeah, it is really e to the minus 3x. So this is the f of xy, y prime equal minus 3y. So we can use the package inside Sage Math. We can use our own algorithm. And let's analyze the local error. Okay, so the analytic solution for the y prime equal y prime equal what's that? sorry, y prime equal minus 3y. So y prime equal minus 3y. To be able to use the DE solve, we should put everything on the left-hand side. So that's why y prime minus minus. So I know that it's positive. So, but anything, I just wanted to say that I will gather everything on the left-hand side. So y prime minus f of xy equals 0. Initial condition, so it will give me the analytic solution. So analytic solution, I will save it in this with this name, and I can use this analytic solution of the I'd like to evaluate analytic solution of the 0.6. It's here. Okay. And the first error using the, can I use this one? Yeah, this one is 0.6 by using step size of the 0.1 is this guy. So analytic solution, which is this guy, minus this guy, which comes from here. Yeah, it's the, yeah, sorry, it's with the use of this guy. So this one, and it's this one. Okay, so it is this one. Sorry about that. I thought that 1/10, um, because it's written first there. So error with a H, step size of the 2/10 is this guy. Error now using the my favorite one is like 0.1, and it is really this time using this number here. Copy, paste here, it is this one. Now let's um, first error divided by the second error. I get this one. Okay, so this is the expected one in using Euler method. So global error truncation in this one here is big O notation of H. So you see that I did the same thing, same question for part the question one. Can I just use this one? OH, it's this one. We just practice the extra thing. We can see the other thing, like you can see the local error is OH2 if H is gets finer in like using the improved Euler method. Okay. We can also see the, so in global error for improved Euler method is like this one, and local error for the classic Euler method is like this one as well. Okay. So it's possible to see these things, but like not here. So this example for test verifying global error of the Euler method. Okay, so I have also developed a new simpler Euler, which I have discussed it in week 8. So it's possible. So you can see these things as well. And also you can, in your second assignment, you can use vector fields. So the vector field command should be around somewhere here. Okay, this one. And it's kind of confirming the solution. So for y prime equal minus 3y, so the converging for Euler method, the step size h should be like 0, really less than 2 over 3. Okay, 2 over 3. So if we choose step size like 0.7, it will be this red and diverging. So it's not converging, it's not working. But if we use like step size like 0.2, like less than 2 over 3, it will be converging. It will be converging here. So step size of 0.2. So it is green one. It's this one. So it is really converging. Okay, so other examples. It's the same thing like step size of the 0.7. Here, same plot. you can use the backward Euler method. It's the command is here. For the backward Euler method or just implicit. So we can call it again implicit Euler. So you can still use this one, but this one K1 should be modified because y prime equal minus 3y. Then you will write yn plus 1 equal yn plus h times f of xn plus 1 and yn plus 1. So you need to solve the equation for yn plus 1. So once you solve it, you will see that the k1 is there will have to be this guy. So you will not use this backward Euler method in your assignment. Okay, so this file is anyway is available, so you can still use it. It's the same example thing here. If you use backward Euler method by choosing step size of the 0.7, where forward Euler method didn't work, it works with the backward Euler method. So you see that the red one is converging. All right, that's all for today. I hope the question assignment 2 will be easy for you. Just you can use the Sage Math cell here. You see that it works. So if I compare it by this one here, it's this one. Is that really this one? Yeah, it's the same thing, 1.5 using the step size of the 0.1. So 1 point. So can I compare the numbers? 1.82. Yeah, it's really the same thing. So all you need, just put this one here, all things here. It should be the same space using tab or space button, and this command means like this guy comes after this one. So the only bad thing of the Sage Cell server, you need to write everything on in here. And one thing, if you have no longer access to the, if you don't have access to the Jupyter notebook, so say, let's assume that you don't have this one. So, but you've got the PDF one here. Okay. So don't do this one. Don't do like copy Sage Cell. It's not working. See, if I copy this one, so it will be mess. It will be bad. So let's Control Z. And how about this one? Copy with formatting. Okay, it worked. So let's get everything from here. Can I get that? Okay, this one, it didn't work. So sometime, okay, so let's do this one. So how about 2 by 2? Copy formatting, Control R, deleting everything. It's this one. It didn't work as well. So what you will do is just get this one, and this one should be in this one. So if I were you, I would just get the copy line by line. Okay, it didn't work. Still, copy with formatting. I will do this one. Paste and match style. So just remove the quotations, then come here under E. So I won't be tricked. I will just copy this one. Copy this one. Even it doesn't work since it's just a couple of the line. Okay, it works. So I will come under this one and I will do one by one. So all you need, just copy and paste one of them. It takes some time, but it is easy. You can do it. And The last and but not least and important is this one. Uh, if you the Hume's method is given in the lecture notes, so you should use the Hume's method instructed in the uh, from the context. So do not use the Hume's method by in the Wikipedia. Okay, that's the last thing, and the Hume's method you can just modify this part. Question 3. Just need to modify this part for Hume's method, and I'm pretty sure that you will be fine. Okay, all the best with your assignment.